Welcome everyone to this webinar. Today's host is me, Anders Bresell. I'm heading up the Development and Data Science Department here at Telenor Connection. And I am today going to speak about design considerations for your IoT solutions. And I will do this from a perspective of reasoning around hot and cold data. I think you will be muted during the presentation, but we will open up for questions at the end. If you want to stay, I'll get them online here in text, so I can address them afterwards. And otherwise, we probably will collect the questions that remain and see if we can address them at a later stage. So let's get started. Welcome everyone again. And first slide is this very standard one. We have the value of data versus the latency or the real-timeness, so to say, where we at the right-hand side have this traditional batch business intelligence reporting sent to the management once a month. Not has moderate value, but if you move down to latency around like maybe 1 hour or 30-60 minutes or something like that, we can start to be reactive. At least we can observe something, something going bad, and we can start act on it. But when you move closer to the boundaries of the latencies, or maybe one minute or something, it sort of makes sense to be really actionable and really change the course of outcome. For instance, if there is a disturbance, you can make an action to not get escalating value, negative effects of this. You monitor, you alarm, you act. You cannot go even further down to the real-time domain with milliseconds and so on. But there is, of course, this concept of predictive and preventive, but that's a little bit different, because what you do there is you monitor stuff as they are now or the past period, and then you sort of predict what will happen the next minutes, next hours, or something like that, and take actions in order to steer the future, so to say, and like probably prevent stuff that is negative events to happen at all. So that's sort of it. But we will move around this axis today. So the question might be, how fresh is your data? And if you use this hot and cold, where hot is sort of real time in some sense, very, very, very real time, it's always a gradual scale where someone will say real time is near real time and so on. But I will not really go into those definitions. It's not of importance today. But if we reason of this as a spectrum of hotness or coldness of data, we are driven by the fact that how often actually a data point is produced. So an analog sensor will always have value. So whenever you read out, you will have a value. If you have a digital sensor, it can produce a value every second or something like that. So that's your limit of your IoT solution, the fundamental limit, so to say. But then you can decide if you're going to send every single value every single time, or if you're going to wait a bit and only send like every 10th value, or an average over the past 10 observations or something like that. That will have some different impacts on your IoT solution. You can also do like aggregates, so you like you send the total. If you have a door that opens and closes, and you count the number of times someone passes the door, you can have a counter. Then you can send the aggregated value every 10th or minute or something like that, and with very small volumes, rather than sending every time those persons pass the data, pass the door. So the important thing here is that you need to understand this hotness and coldness of data, and consider this in design of a solution when you think about automation and applying your business logic, because that will be very critical. So why does this matter? Well, first of all, it will put requirements on your onboard hardware. And if you wait a bit and don't send all the data and just send small amounts, maybe you can be smart about your traffic costs. But on the other hand, if you send a lot of data, it can likely drives and increases your compute cost, and probably that should be linked to a value somewhere in your IoT solution. But the way you design and decide on hot and cold data also determines your ability to automate things. And I hopefully can showcase this through some use cases later on. But I think this is a very critical thing. These different decisions on how you will process your data, what boundaries you will set, if it will be hot and cold in different aspects in different parts of the solution, will enable or even inhibit any further innovations of your IoT solution. So let's look at a few use cases, but before we do that, I want to go through what I call the technology stack, and that's like a conceptual way to describe the different technical domains that we need to drill down to understand this topic a little bit deeper. So given that we now have a device, in this case it's a lawn mower, and we have a modem because this is cellular-based connectivity, then you can do your data transfer. In order to receive that data somewhere, you need to have an ingestion flow, and that typically connects to your IoT backend, where you have your digital twin of your connected device. And there you also maybe have some simple rule-based business logic saying, if it's online, send a notification like that. So this contains the current state of the device in your IoT backend. But over time, you probably need to offload all this ingestion data and all the sensor values into a data warehouse where you can do queries, reporting, do analytics, and so on. Normally, the IoT backend is your operational, your functional unit, while the data warehouse is something where you collect data and crunch it and derive insights and so on. But if you talk about IoT and big data, and that's normally associated with this, you don't also need to talk about data lake. I will come back to this in a few seconds. But most importantly, I think you need to consider also the automation of your business logic. So that can be put somewhere in this technology stack. It can be in the device, it can be in your ingestion flow when a value comes in, you do something, whether if it's above or below something, some threshold. You can also do that on change values in your IoT backend, or you can maybe even do that in your data warehouse if you're doing reports or API calls towards it. But that's normally really not the best design. But yeah, there is various ways to do that. So just a side note on data lake. What you need to know here, data here is on disk. It's a cheap way, and the purpose here is to save the data for later. So you can do searches of the data to your data lake, and the purpose is mainly to derive and compile data sets, so you can create data sets for your deep learning models and your AI machinery. But I have seen no good cases where you actually put your automation business logic. It's sort of not that kind of architecture that allows that. So remember this, you learn, but you don't automate using your data lake. But you save it for later. That's the purpose of the data. So again, the data and the technology stack here, and where are we in the hot and cold space? Well, the device is normally constrained in some way or the other. It doesn't have infinite storage capability or memory or compute capacity. So you can only store some data from the sensors or the actuators locally for some time. At some point, you need to remove to replace to get headroom for storing new values. So as long as you keep data buffered on your device, you can also select that time frame when you do your data transfer. So that means also, of course, that the ingestion flow will have that. And if you talk about the real-timeness or the update or latency in your IoT backend, that's of course connected to the ingestion flow. But at some part there, you can also move data over to the data warehouse. Data warehouses are databases. They are normally not designed to handle real-time data flows. So normally you need to do like batch updates there or something like that. But you can store data for some more time, but it's still a costly solution. So maybe you will go into the data lake either from the ingestion flow or as offloading from your data warehouse, where you can store much more data for historical purposes. Going back to that later. So there's the automation business logic here. I sort of limit to, you can stretch it out to the data warehouse, but not really further. It's mainly limited to your device or ingestion flow or IoT backend. But you also have your consumer business application. It's just one case here, but it can be your smartphone application which is your interface towards customers, but it can also be your ERP systems or internal customer management systems. Something we would consider internal systems if you are a corporate. So, first use case, pet tracker. Very simple concept. There's a necklace around the dog that sends the coordinates, and those are visualized in the smartphone app, so the dog owner can see where the dog is if it runs away. So in this case, the geo coordinates are very real time. They'll send every time they're updated. They will be sent. So you send it directly to an update IoT backend where you link the necklace to the customer, and then of course I'm indirected to the dog. And the smartphone application with the map will update the coordinate based on a push notification from the IoT backend. So that is the very simple use case. There's no real automation here. It's just a push of real-time data into a consumer app. There's no business logic and so on. What you see here is what will result in quite high data transfer cost. You need to send everything you observe, you need to send at once. But there's no really high compute cost. You just forward a value and you don't store it, so there's no storage cost. So in that sense, it's very simple use case and maybe relevant in some context. The next use case is the smart meter. So here's an electricity meter mounted in houses or buildings. So the purpose here is to collect and report the energy consumption in order for the energy company to send in monthly invoices to the customer. So the whole purpose here is to actually remove that step where you need a human to read out the values from the meter and then manually enter that into some system that you then can compile your invoices from. So I call this just dumb smart meter because the smartness is not really there, but there is a case where you remove the human labor of actually going out and read out the meters. So, okay, you need to, in this case, report the consumption very often in real time because everything that is measured, the only thing that you measure is the thing you can invoice. You can't make up consumption. So you need to measure everything, and that's sort of real time. But what you can do is that you can wait once a day, or even once an hour, or once a day, or even more seldom, to report the consumption over the day from the device, because the only time you actually need the data is the end of the month when you compile your invoice. So then you can throw the data up to the ingestion flow and directly into your data warehouse where you do your aggregations, you do the query to the data warehouse, update your invoicing system with a new row. This customer has now consumed this much energy for this month, and the invoice will send out. So the trick here is that you actually buffer data locally in the device. You send only once a day and so on. But there's no actual business logic automation. You don't remove that many humans from the actions here, except for the initial thing with actually manual readout. But that's not even IoT. So what you see here is a very low data transfer cost. There's very low compute cost and rather low storage cost because there's very few measurements. And you can even have a counter or like 3 parameters on the device, like the current value, the last value, and then you sum those two into the aggregated. So it's very good for constrained devices, this use case. But if you move into the more advanced cases, sort of what I will call the intelligent smart meter, here the idea is that you are an energy company, you have your energy production units, maybe solar panels or something like that. You have consumers that use your energy, And you can even buy and sell on the spot market, because maybe sometimes you produce too much, more than you need, and you can sell it, and sometimes you need more than you actually can produce, and then you need to buy it. So the idea here is that all the households in your customer fleet here reports the consumption in real time, and then you use a central artificial intelligence that buys and sells the power on the spot market based on a prediction model. Given the current pattern and the current day of month or day of week, we probably need more or less power next few minutes or hours, and then buys and sells accordingly. So let's see how that's looked like from the technology stack. Well, first of all, you need to sample the consumption in real time. You need to also transfer it in real time and update that in IoT backend, so you have the current consumption of all the households. From that, you link that to your business logic, which will probably a deep learning model predicting the energy price on the spot market, the consumption in the next hours, and so on. And then you have the business application that actually puts the order towards the energy market. But in this case, you probably also need the consumption and the performance of the system stored in the data warehouse, so you can follow up. Do you need to tune? Does it do its job? Is it gradually degrading in performance? But you probably also need to store all the consumption in the data lake, because you probably also need to relate this data to weather data or seasonal data, wintertime, summertime. Is it raining? Is it windy? And all those affects the housewarming need, and of course also the energy consumption. So here you have real-time data. You learn from history, you predict the consumption, and you optimize your spot price. And then, yeah. So this results in rather high data transfer cost, very high compute, because you have an online prediction model that you need to host, and you have a lot of data to process through this engine. And you also need to store all of this data to make sense of it and improve and make sure that the prediction model is accurate. But overall, hopefully this business case is a good one, and then you go for it. Another use case is the unauthorized usage detector. My concept here is maybe you have an home alarm with a central unit turned to the left, and you want to detect if someone is tampering with your alarm system. So it's not supposed to be opening should open the cabinet, and if someone does that, you need to be able to detect that instantly. So you might have a sensor just for that inside your cabinet. But under most days, most months, most years, there's nobody opening this. So you don't need to send that much data in real time. But when something happens, then you need to alert very quickly. So let's look at this use case. First of all, you need to be able to sample this event, the open of cabinet or this fraud, instantly and in real time. So that's what you do in the device. But you don't need to send all the time when nothing has happened. So you can only do a data transfer and sort of a ping saying a heartbeat. Hey, I'm still alive. I have power. I'm functioning, and so on. So no problem, no worries. And if something will happen, I'm able to report. So that's what we call a heartbeat. But if something is happening, then you need to be able to act very quickly. So you need to update the IoT backend with the latest state of this alarm unit, and of course you need automation directed. So now someone needs to be alerted. Maybe it's the home alarm owner that gets a push notification to a phone, or you even send out a technician to look at this, or even some security personnel that needs to check if there is a thief or a burglar somewhere that tries to tamper with the system. So here you actually have sort of a local prediction model. Even in this example, it's a very simple one with a sort of 1 and 0, on and off, is the cabinet mounted or not. But you can also think of a more advanced model here, prediction model of fraud. So that how many times is someone pressing the numbering panel there? Would that indicate that someone is trying to brute force it by pressing many codes or something like that? That is something you maybe want to detect and alert on. That requires much more capability of the edge, and you need to push a model down there that can detect this usage pattern. The key here is that you send not that much data, and you have the heartbeat once an hour. But here you need to think about how you get training data for this model. Here you probably need to investigate in a way to get some samples, some normal circumstances, normal usage, send some portion of data up to your central system so you can learn from that, but also sample more data than just the event that triggered this anomaly or this fraud alert. So you sample some more data before and after to make sure that you get a lot of data to train and upgrade your model and improve it. Because if there's something that is quite common for fraud, is that if there's a fraud and someone discovers it, the one that managed the system sort of tries to, or are very successful in blocking that specific fraudulent behavior. But what a fraudulent actor is doing is that looking for new ways to come into the system. So you constantly need to update this kind of model. And then you also need to be able to figure out how you can develop a model centralized by looking at all your home alarm systems fleet around many, many houses, collect that centrally, derive new models, and then you need to push out the model down to the devices again so you can keep them updated. And maybe I can touch up on this later again. But yeah, that's the concept. So this is very low data transfer cost, but it's expensive edge computing, and you don't need to have these excessive amounts of data as in the smart or this intelligent smart meter, smart grid concept. My last case here is the automotive on call. So this is a car that is connected, and the car owner has an app. The app means that I as a consumer can go in that and configure. So every morning at 7:30 I will leave from work, and by then I want my car to be warm. So there will be a scheduled push down, and the car will then regulate the heat of the car to make it warm and make sure that there is no frost on the windshields and so on. So it will measure the outside temperature and schedule this in an effective way. But you also get like a dashboard that you see in the middle where it says, okay, what the temperature is in the car right now, is it locked, how long was my last trip, how long can I go with the fuel in my tank, and so on. That's not much data that you actually need to send. You can aggregate this locally in the car and send that up after your drive. You don't need to send this in real time to be able to provide this user experience. But what you also can do with this concept is that in the backend, you can also do of the car, you can measure a lot of wear and tear and the usage pattern and distill that to a few performance indicators, which you send up to the backend, and you store those for historical purposes. And from this, you can actually do predictive maintenance and build a model and move away from a scheduled service window to demand-based without jeopardizing the customer experience. So that's quite neat. And you can actually do this with a kind of a simple setup, and I will go through this. So first, you have this end consumer thing where you, from the app, rather push down a configuration, and the car will start behaving in a very nice way. But you also have this business intelligence, the dashboard that you see as a consumer of how your car is driven. But you also have this predictive maintenance, which then you constantly, after every drive, you get updated data on how the car is, the health of it, and you can do predictive maintenance and say for how long will it be able to drive this without actually going to service. And if you see that some car has been changed in behavior, maybe you'll schedule a service window, maybe even order spare parts and so on, and have a really neat customer experience from that perspective also, or deliver on your customer promises or warranty or something like that. So in this case, you really have quite low data transfer cost. It's just aggregates you send up or a configuration, but it's sort of quite advanced anyhow, and you don't need a very capable edge device. But in this case, of course, a car has an onboard computer that is quite advanced. But from a connectivity and action based on what you send and report from the device, it's not that costly from an edge compute perspective, and you don't have that much data either, but you have the valuable data that is that makes the difference. So what I want to bring out from all of these use cases, I think that from many experience of many of our customers, I mean, every use case is unique, and that is something that makes it sort of difficult now to design your IoT solution. There's so many different questions that you need to address and think about. But if you reason in your IoT design around hot and cold data, I think that can really help you in most of the design aspects of your IoT solution. Whether it's about how often you produce your data points, what the capabilities need to be on your edge computing, or the latency requirements and the cost or effectiveness and amount of data you need to transfer, the requirements of reporting and follow-up, and mostly important, where it actually makes a difference, is the actions and the automations. So data in itself has some value, but it's not until you do insight from the data it's value something more. But when it really makes a difference is when you take actions based on the insights. So you need to close the loop. That's where you make it a business case. So automation is taking actions in a systematic way, in a scalable way, rather than involving a human to be notified that nevertheless needs to drive somewhere or do something. And humans are we are many, but we can't scale that fast as machines, and automated actions like software can do, and predictive machinery. So someone tells me here that we are don't have any more time, so I would thank you very much for listening in. Hopefully there was some good learnings for you, and we have some questions, and we'll see if we can share those with you guys and girls afterwards. So thank you very much, and have a good rest of the day. Thank you. Bye.